14.6 bases now. For this one, the worksheet, I want you to do number 1, number 2A, and 2C, and number 3. Now, number 2B. If you want to do number 2B, you can. It's really not hard. It's just kind of time consuming. And it's kind of like a problem I talked about in the previous video where like a busy work problem, okay, I do all this and do all this. But sometimes they ask you something like that on AP. I would say look at it at least that you kind of see if you have an idea of how you would do it. Read it. Think about how would I do that. You might want to just put a little note to yourself. I don't care. If you don't do it, you don't do it. But you can read it and just say, oh, I would need to do this and this and this. Okay. And then when you see the answer key, you can actually study over that if you want. Or, hey, if you want to do it, do it. Because it won't hurt. Every now and then they ask you a little problem like that. That's like a little, one thing that might be a little, time consuming thing. Okay. This, oh boy, I hope my chalk is okay. Chalk, where are you? Oh, do I have a new chalk? Oh, yay. Oh, good. My chalk was getting broken. All right, this ought to be pretty easy for bases. A lot of this will kind of be parallel to what we already learned with acids, and you'll kind of say, oh yeah, that makes sense. It's not that hard. I kind of told you a lot of this already. On that worksheet, I forgot to tell you, number 3, you're not going to do number 4 on the left side, on the right side of that paper on the back. Well, the other page, second page, yet. You're not going to do it yet. You might know how to do some of it. You might remember it because I taught it already. But I'll talk about it. It actually goes with the next lesson. I think I just put it there because just to save paper when I print them out, it goes with the next lesson. So only 1, 2, 3, and you're going to skip 2B. Okay. All right. All right. So bases, we said the Arrhenius definition were substances that produces OH when they're put in the water. And so, but the Bronsted, that's a bigger deal. Yeah, okay, this is just I'm just kind of reviewing the first lesson we talked about. Arrhenius acids and bases. Acid is something that gives you H plus in water. Bases give you OH. Well, this is more important is the conjugate base, conjugate acid stuff. Bronsted-Lowry definition. A base is a proton acceptor. So an acid, a proton donor. It donates H plus, but a base is anything that the H plus attaches to. Anything that receives it, accepts the H plus. All right, so the first part, and this is also just a review. I don't know why. Well, it might be in the book too, and a lot of times I was doing this by the book. Identify each of the following as proton donor, proton acceptor, acid, base, conjugate base. Let's just look at it and see if I can do it this way. We know HCl is an acid. We know NaOH is a base. So, we can use that one. Acid, base. That's not too good. So, on the other side, when maybe you do want to do the... let's just do it. Okay, HCl, NaOH. I think we already did this exact one. HOH, NaCl. If you already know it, you can just go past it to the part that is new. We know that's the acid, that's the base. Who loses the H plus? The HCl. So it's Cl negative. That really is your conjugate base. Really, I guess it helps to put out like a net ionic. Cl negative is your conjugate base. And then the OH gains the H right here. So this is your conjugate acid. So acid and its alter form, remember when the H comes off, that's the conjugate base. Really, the OH is really the base, the OH negative, and then the HOH is the conjugate. I guess it helps if you think about the net ionic equation. Really, well, H plus, actually the ionic equation, Na plus, HOH plus, what would that be? Cl negative and Na plus. So that's your acid. We'll just say, that makes it crazier. But anyway, that's your conjugate base. That HCl is your acid. Or you can just say H plus is the acid here. That's why it gets weird. Now let's just keep it like this. Forget this part. But this helps you see it. And this you can see that OH is really the base. You can say NaOH is the base. But OH, and then the conjugate of that was HOH. Okay? All right. B, HCl and NaF to give you HF NaCl. There's a reason why we're doing this. It's going to matter in the next lesson more. So I'm not exactly sure why it popped up here. That's your acid. So this must be the base. And you would think, well, why would that be a base? I don't see any OH or anything there. Well, think about this. F on this side, think about it, F negative. And it's going to gain the H over here. The H donates from the acid, and it attaches onto F. That's your acid. So that's your conjugate. I'm sorry. That's the conjugate. That's the conjugate base. The Cl without the H. But now, who does the H go to? It goes to the F. So this is the base. And then this will be your conjugate acid. Sorry about that. All right. And then the last one, HCl and water. And this is just giving you that dissociation equation. But even in that, it would technically be 2 arrows there. This is actually probably easier. Acid, and then... Wait a minute. That's a messed up. That's a mistake. Oh, well, yeah. Vela, what are you doing? Cl negative. It's still easy. That's your acid. It wasn't OH. I went crazy there. That's an acid. That's the base. Conjugate base. And that must be your base. That's the acid. Acid reacts with base. So there's always acid base on the left, acid base on the right. Acid base, this is your base, that's your conjugate acid. Okay, that was a little review. I don't know exactly why I popped it in there, but oh well. Not a bad thing to have a review of it. All right. So, a strong base is any substance that has OH negative that dissolves in water. So if it is soluble in water, then it is a strong base. If it's a soluble hydroxide. Now, if you remember the solubility rules, you kind of know this already. None of the hydroxides dissolve except for group 1. So look at the group 1 on the chart. Everything in group 1 dissolves. These would all be strong bases. Lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium, francium. All these, not water though, but all of these OHs are going to be strong bases. But you know what? The only 2 that you're really going to hear about are, the only 2 you're going to hear about probably on all of AP is just sodium hydroxide, potassium hydroxide. It's probably all they're going to mention, but all of these will be strong bases. And of these, the camel with straw on his back, calcium hydroxide, strontium hydroxide, barium hydroxide will be counted as strong bases because they're soluble. Now, there's a little bit of debate between different chemists about whether or not these are soluble or they're not as soluble as some things. So you probably aren't going to see those because of that reason, because it's kind of a debate about it. But all right, that's all the strong bases. Anything else would be a weak base, and the main weak base that you're going to hear about, there's really 2 of them. One of them is ammonia, and I didn't put this. Let me see. Oh, and I also mentioned that NH4OH is not a strong base. That is not a strong base, okay? Even though it's soluble in water, because it doesn't break up all the way. This actually becomes ammonia itself, which is kind of weird. We'll show you it's an ammonia equilibrium. But let me tell you about these 2. Here are the 2 most common bases that you see on AP that are weak bases. Ammonia, because ammonia, when it reacts with water, we're going to see this probably on the next page, but I'm doing it now anyway. When it reacts with water, it gains an H. It's a base. So it becomes NH4 plus, and then water is left with OH negative. See, you might want to write it like HOH. H attaches there, NH4 plus, OH negative. So obviously, when you put ammonia in water, it ends up being basic. OH negative is produced. Okay, so that's a base. And the other one would be this. It's an organic base. And I'm going to do one like this, I know, in a moment. I'm just going to tell you right now so you know. If you can have anything with carbon and hydrogen, any number you want to have there, CX, H, Y. But then what you're going to have attached to it, the amine group, NH2. So it could be any, C4, H6, NH2, or H5, NH2, whatever you have. But this is a base, because here's what it does in water. In water, and there are many of these, The H comes there, and you get C. I'll just put X, Y, NH3. So it gains an H, makes you NH3, and it's plus 1. Just kind of like that, gain 1. NH3 gains 1 to become NH4 plus. But the NH2 gains 1 to become NH3 plus. And then, of course, again, you're left with OH negative. These two are probably the most common. But now you also have, and it's really the next lesson, but you have conjugate salts that do the same thing in water. But I think I'm going to wait till, if that pops up in this lesson, I'll talk about it. If not, it'll be in the next lesson. But these are the two most common bases that you'll see. Like if for some reason this year on the AP they were to ask a question on a weak base equilibrium, they haven't asked that in a while. But if they were to ask that, it probably would be either that one or that one. And this could be, this could be any number you want, any number there you want to put. It could be like amino methane, amino ethane, amino propane, whatever, anything like that with the amine group attached to it. All right, and okay, so I just wanted to show you those two reactions. You should be aware of those. Now, I mentioned here antacids. Many things like MgOH. Many antacids have like magnesium hydroxide, aluminum hydroxide. They would be very strong bases and would damage your mouth and your throat and your stomach. But since they're insoluble, it's okay. Kind of interesting. You swallow those MgOH2 and it doesn't dissolve in your throat or in your mouth anywhere. It gets your stomach. But then in your stomach, where the acid is, that's where it will dissolve. But the good thing is it will dissolve and it will neutralize HCl. I think I've mentioned before that HCl is actually in your stomach. I think I may have told you that before, hydrochloric acid. But it's surrounded by fat, and so you're safe. You're safe from it. If you could take the HCl out of your stomach and put it on your skin, it would burn your skin. Bad, dangerous. So magnesium hydroxide could go in there, and OH negative plus the H plus would make water. It would neutralize it right there in your stomach. The insoluble, the solid would go in there and it would react with the acid. It would dissolve in the acid, but then it would neutralize it. Okay, it's kind of an interesting thing. Calcium hydroxide called Slate Lime. This can be added. This is just something interesting you can read. Can add the gases that come out of smokestacks. SO2. Okay, so sulfur dioxide can form H2SO3. And then H2SO3 can react with the calcium hydroxide to make calcium sulfite. I guess it'll be it's safer. Basically just like an industrial, environmental help. We don't have to worry about that. Okay, weak bases. Oh, and here's the next page where I talked about what I mentioned. As mentioned previously, many bases do not contain OH negative Bronsted bases. Some of them are weak non-hydroxide. NH3, that's number one. And there's the equation I told you about with NH3. And you also, here are some organic ones. So when I told you C, X, H, Y, well, all of these would follow that. Methylamine, CH3, and an NH2. Okay, here's two CH3s with the NH. Well, now that one, okay, now I didn't tell you about this one, but you should know this anyway. It's kind of an organic thing. This could still join, one H could still join on to that N and make it, so this would be, I don't know how you'd write it, but CH3, well, just look at this formula, CH3, NH. Okay, I can do it this way. CH3 to NH. That would be a base, because here's what's going to happen. When you put it in water, it's going to give you CH3, 2. You're going to have the same thing you see, but another H will join on to that. And since another H will come there, it will become positive. And then you have OH negative. Now, this is more advanced, but they could do that. They could give you that structure on AP and say, how would it react as a base? And another H. So if it's NH2, it will gain one more to become NH3. Just like if it was NH, then it could get this. It become NH2. You could even have 3 of them on there, I think, and then have CH3 with no, and then it becomes NH when one H joins it. So that's crazy, but I haven't really seen that. Oh, and it is right there. I didn't even see that. Trimethylamine. So that one, well, I'll do that one too. I didn't even know that this was in the notes here. This would be a base because when it reacts with water, it's going to go become CH3 another H will join onto it. One H will join onto it. So just kind of get that little pattern, but it's not that hard to see. Okay, and here are the KB values, and there's even one called pyridine there. Don't worry about. I wouldn't worry about these ring structures, organic stuff. I wouldn't worry about that. But these you can see. Okay, ammonia, methylamine, and this is what I was showing you on the board a moment ago. But ethylamine, ethylamine, all of these NH2s in water will become NH3 plus. But then this last one, I didn't see that was on there. It has only one N on it, so then it can just join one NH plus. So they can still give you that formula. Don't be afraid of that. N becomes the NH plus, like this one you see here. Well, that isn't really pyridine, but oh well, it's okay. Okay, but it would work. You just follow the formula that said there. All right, now strong bases. Identify the major species present and calculate OH, POH, and pH for all these solutions. I don't even worry. Again, this is something from your textbook about identifying all the pieces. They're going to tell you that. On AP, they're going to ask you, hey, what's the OH concentration? What's the H plus concentration? Tell me that. So the first one, let me see if I want to do all these or not. You know what? I did it for the acid, but I don't really want to do it for this one. But I'll do this. I tell you what. Here's what I'll tell you. If you have a strong base like KOH, the OH negative will be equal to the strong base molarity. So I'll just tell you this. For A number 1, the OH negative concentration, it's a strong base. For a strong base, the OH will equal the original, how do they write that? Base OH? Well, I'll just put it KOH in this case. If it's a strong base, the OH will equal the molarity of the KOH. So, if it's 0.75 KOH, I guess I better do it. Yeah, I'll do it. If it's 0.75 molar KOH, if KOH molarity is 0.75 molar, then that means then the OH negative molarity will also be 0.75 molar. So, if I want to find, what they really ask you on the AP always, and you'll see, is not to find the POH, but usually to find the pH. So, if they give you OH, they want you to find pH. So, the way you can do it, first I'll say, what's the H plus concentration? So, I know the OH times H plus, sorry, what a mess, I'm writing this so bad, is equal to 1 times 10 to the negative 14. So 0.75 molar times the H plus molarity is 1 times 10 to the negative 14. I told you that most of this will probably look pretty easy. Probably just what I told you a moment ago, that weird stuff about the organic bases. That's probably the only thing that you didn't know yet. But most of this probably will make sense. So the H plus would equal 1.3 10 to the negative 14. All right, so 1 times 10 to the negative 14 divided by 0.75 is 1.3 times 10 to the negative 14. Okay, so that's your... So in this solution, KOH, if KOH is 0.75 molar, your OH is 0.75 also. Your H plus is 1.3 10 to the negative 14. And calculate pH and POH. So pH is negative log of H plus, which is negative log of 1.3 10 to the negative 14. So 1.3 E14 negative, get the log negative, it's 13 point, and you have 2 sig figs in this number, so after the decimal 2 sig figs, 89. 13.89 is the pH. So, remember POH, pH plus POH is 14.00, so if that's 13.89, just subtract it. I mean, you don't have to write an algebra equation. You can just put 14 minus 13.89 if you want. But okay, so 14 minus 13.89, it's 0.11. 0.11, that makes sense. That'll get you up to 14. So 0.11 is POH. Now, another way to find POH is POH, or you can do this, is negative log of the OH negative concentration. So negative log of, and the OH is going to be, what did we say it was? Oh, 1 times, no, 0.75. So 0.75 log negative, and I get 0.12. So they're not, they're a little, they're okay. It's not, didn't matter, a little bit off. 0.12. So if I were to get the pH, now say 14 minus 0.12, and it's going to be 13. I got 13.88. So that doesn't look quite as bad. The pH 13.89, 13.88 if you go the other route. So there's a little bit off. So that's just the basics. That's the basics for the base. Okay, pH, POH, OH plus. OH negative and H plus. Find all 4 of those. Now, if it's a strong base, that's all you got to do. Like we talked about that with the strong acids, it's really easy. HCl is a strong acid, so if I've got 3 molar HCl, then my H plus is 3 molar. If I have 0.75 molar KOH, since it's a strong base, then my OH negative will be 0.75. Okay? And when it's a weak, you got to do the ice box, and we're going to jump to that in a minute. Now, okay, so number 2, it says, what if you have strontium hydroxide, SrOH2? All right, well, technically for that one, since you have 2 OHs there, then can you see that even though your molarity is 0.050, you've got double the amount of OHs. So it will be you would double it, 0.0505, so it would be 0.100 molar of OH. That would actually be, if you had strontium hydroxide, your hydroxide would actually be double that times 2, 0.050, how would you say, times 2? Well, 0.050 moles of, well, I hate to do all the math of this. I didn't want to do everything. SrOH2. If I want to convert that, mole per liter, I could just make it mole. 1 mole of SrOH2 is 2 moles of OH. So you can just see that there's double the amount. So it's going to be 0.100 molar of OH. So then that would change the pH. Okay, I don't think you're even going to see strontium hydroxide. I don't think you'll see that one, especially for AP. But if you did, that's what you would do. And then on number 3, there's the busy work problem. It's kind of like the one on the worksheet. I said if you want to do it, you could. What if you had 0.75 molar KOH and it was 0.050 molar strontium hydroxide? I'd have to I couldn't just do it as I did here on number 2. I'd have to actually find the moles, add up my total moles and my total volume as well. That mixture, it should have told you the volume. So when it just says, if it just said mixture there, then I would say, well, yeah, you can assume you had 1 liter, but you'd have 0.75 moles of KOH, but then plus 0.100 moles of OH negative that came from the strontium. So yeah, it's just math. You got to add up. You'll see a problem worked out like that on my answer key if you want to do that number 2B I told you about. You can try it or think about it. I mean, I really doubt they'll put that. The acid one, if AP did one at all, a busy work, add up all the OH pluses of these 2 acids, 2 strong acids mixed together, then find the H plus, add them up, then mole per liter. They would be more likely to do it with acid, strong acid than strong base, I would say. I won't even do that. Okay. All right, now, and I'm not going to make you do it either, but you could look at it. Okay, now here, this is a big deal. pH and POH calcs for bases. I should have said for weak bases. There is a general formula for bases that looks like this. I don't really use it a lot, but you will see it pop up. I'm going to show it to you a little bit later on in another equation. You're going to see B. B stands for base, and what a base does is it gains the H plus, and then of course you're left with OH negative. But that's a little reaction you see on your paper, and I think sometimes AP could give you that reaction. They could. They sometimes give you problems in a symbolic form. Like, for example, an acid, they could just say HA gives you H plus and A minus, or they could give you HA plus H2O gives you H3O plus A minus. They could do this. All right, it wouldn't be crazy if they did that. Okay, but don't be afraid of it. Okay, anyway, but like for example, might say you have an unknown base B, and it undergoes this reaction. They give you all the information, and they want you to find Ka or something, and it doesn't matter. Just treat it like you would any other. But this is the generic form for base, like to represent any base. So the Kb will always be. Remember, you don't put water in it. It'll be the BH plus molarity. That's the form that has the attached hydrogen proton, hydrogen ion, times OH negative over the base. So there it is. And you see that. So you could see that as a general form. And again, H2O does not go down there because it's a liquid. But that will be aqueous, aqueous, aqueous. Like, for example, that could be NH3, that could be NH4 plus 1, and that will be OH negative. Okay? Like I showed you a moment ago. And, of course, water will be there, too. So the base is NH3, and the conjugate is the BH plus. Okay, like so forth there. Okay, all right. So that's all that means. So now here's a problem. Identify the acid, the base, the conjugate acid, conjugate base. I didn't do that, did I? I wrote that down for you, but I'll tell you what they are. In fact, there it was right there. Yeah, we'll just, well, okay, let's just do it. Okay, B. Do it real quick. If you know how to do it, write that down. What's the acid? What's the base? What's the conjugate acid? What's the conjugate base? And whenever you're doing a conjugate, it might make it easier to write HOH. Okay, but you don't have to. Well, actually, it would be hard. Well, no, it wouldn't be necessarily. But if you had an acid, it'd become H3O over here. That'd be hard to draw it. You can write it either way. I'll do H2O. So it gains 1, AH4 plus. So take one H away, and now it's OH negative left. This is your base, okay? You just have to know that's the base because it's going to gain another H. So look over here, it was H3. Here it's H4. It accepted the proton. That's your base. So that's your conjugate acid. That would be your, if that's the base, that's got to be the acid. Remember, there's always an acid base on each side. So that would be your conjugate base. And it's easy to know that's a base, OH negative. Okay, the Kb expression for that one is going to be NH4 plus, the conjugate times OH negative, over NH3 molarity. Okay? And then it just says for a weak base, same equilibrium method applies. Maybe best to calculate pH. Okay, yeah. Well, you have to, actually, what I was saying here. All right, so let me do this. All right, finally, I'll do letter C. And here we go. And it's going to be that equation. If I had thought about, it won't matter. I could have put it over here in the corner like I always do. So whenever I do a problem, you see me, I like to I go from right to left on the icebox on the right side. There is no shortcut for the base. You have to put water in it because you have to show that it got OH out of it. Okay, so let's read the question now. Identify major species present, and that identifying major species, I wouldn't worry about that at all for AP. What they'll do is they'll just they'll say they're going to tell you find the molarity of NH3 or of NH4 plus or OH negative at equilibrium, or H plus. They can even say H plus, which you don't see here, but remember if you know OH, you can always find H plus. Okay, they're going to probably do it that way. The only time I've seen where they say identify a species present after the reaction are the ESP problems. You remember what those are? Like, oh no, I can go back and watch that video from last semester. ESP, whew, crazy problem. Okay, we'll talk about it before the AP, or I'll just go back and watch that video. All right, but anyway, here we go. Find the pH of a 15 molar NH3 solution. So you got 15 molar NH3. Now, it seems like if you had a weak acid and they're going to make you do icebox on AP, they're going to say, oh, find the pH. Okay, you do all the steps, find the H plus, find the pH. It seems like when they have a base, weak base, they're going to ask you to find the POH. I don't think they ever ask for POH at all on AP. And here's why this can be a little bit of a trick, or it can get you. Be careful. Find the pH of 15 molar NH3. So watch. Okay, this is 15. This is 0 and 0. Minus X plus X plus X. So far, so good. 15 minus x, x, and x. Now the KB is 1.810 to the negative 5. It's kind of interesting that that number is the same as the one for acetic acid, if you remember that number, but it doesn't matter though. So they'll say, okay, write the KB expression. You know, they could ask you on AP to write that equation even. Right? Then they could say, write the KB expression, like write the net ionic of that, and write the KB. But KB will be NH4 plus, and then find the pH of that. Okay, OH negative, find the pH, find the pH. I'm going to write that down so we'll remember. Find the pH. Okay, OH negative, and on the bottom you'll put NH3. Okay, so let's put in all the stuff. We know KB, it says 1.8. Does it work when I'm, okay, I guess I'm all right. 10 to the negative 5. I always stand on that side. I know I disappear from you guys, that side. But I didn't know I could actually stand here and disappear. Here I am. Yeah, okay, here we go. 1.8, 10 to the negative 5. All right, X, molarity of NH4. OH is also X. And NH3 is 15 minus X. Then you get to, again, assume X is negligible. Then, okay, this is going to be X squared over just 15. That part goes away. Remember, whatever you add or subtract, minus X or plus X, minus 2X, minus plus 4X, it doesn't matter. But just don't take away this part and don't take away these X's, because otherwise it'll be nothing left to solve for. Okay, so you're saying what breaks off is insignificant, or what is added or whatever. Okay, so multiply that, and that becomes 2.7 10 to the negative 4 equals X squared. You get the square root of both of those, and it looks like 0.016 molar is X. So let me move back over here again. So 1.8 10 to the negative 5. Just going to double check it, times 15. Get the square root, 1.016 molar. Okay, the question was find the pH. So a lot of times, here's the mistake people make. Oh, 0.16, that's X. Okay, so pH negative log, push negative log, and I'm done. But no, that will be wrong. Think about this. What did you just find right now? Always think about it. What did I just find? 0.016 is X. You just found OH. X is OH, not H. And so you might even put a little OH there. It might be good to do that to remind you. If you ever have the base, I know you go through it so fast in the AP. Oh, I'm so happy. I know this. Dude, you fill those in. Fill my spot. Fill it in. Got down to there. And then but just remember, for a base, that's the OH, not the H plus. And they love to do that on AP. They say, find the pH of the base. But then, and everybody just says, okay, pH negative log of that number. They think they're done. They just found the POH, okay? So you could do that. If you wanted to, you could find the POH and subtract it from 14. But you know what I'll do, just to really be safe, H plus times OH negative is equal to 1 times 10 to the negative 14. So I'm going to plug it in here. I'm going to find my H plus and then find the pH that way. You might think it's easier the other way, and you can do it. I'll do it both. I'll show you the other one here before I stop. Okay, so just H plus. Actually, it would have been faster to do it the other way. Well, H plus, so 1 times 10 to the 14 negative. Then I'll divide by 0.016. It's 6.3 10 to the negative 13 molar. That's your H plus. Does that fit on there? I guess it will kind of. Then so pH is negative log of 6.3 10 to the negative 13 molar. And you know what? I'll check it by doing the other one. So it looks like 12.26 figs, 220. 12.20 is the pH. Now, here's what I could have done. This is probably faster. It's probably better if you catch it sharp enough. All right, OH negative. So POH is negative log of 0.016. So I'm going to put 0.016 log negative, and I get 1.02 sig figs. Okay. 1.79, well, 1.80. That's your POH. So then you know that, well, I'll come up here. Not a space. pH plus POH is 14. Oh, I'm going to run out of space everywhere. So 14 minus 1.80 is 12.20 pH. That's probably faster. Do that and do that. Well, I just did that. I took a long time, I guess. Maybe that wouldn't be the best way to do it. I said, I will do it this way. Well, I want to do it here to remind you. What you found is OH. So a lot of people just do this. They don't put PO. They just put negative log of that 1.80. But they didn't get they missed the problem. But now if you did that, then you subtracted it, they'll say, but I would write pH next to it at least so they know what you just found. POH. Writing the POH there might possibly get you a point or something. At least you know how to get POH or half a point, or I don't think they do half points, but anyway, there we are. Okay, now find the percent ionization. So I didn't do that. So remember, percent ionization for acid, it's the H plus divided by the original molarity. Remember? Well, for bases, it's the OH negative divided by the original molarity there. Percent, and they can also call it percent dissociation. But, really, this isn't really dissociating, it's reacting. So now they call it percent ionization. But they have called it percent dissociation before. So anyway, here's how you do it. Watch. I'll just put it right here for part 2 of this problem. So percent ionization. And you can use the word percent ionization even for the acid. These are both interchangeable for acids or bases. Percent ionization or dissociation or whatever is going to be the OH negative at equilibrium divided by the original base molarity times 100. So the OH at equilibrium was 0.016 molar. The base originally was 15 molar. Times 100. Looks pretty small. 0.016 divided by 15 times 100. Really small, 0.11%. And make sure you put in your answer 0.11%. If they ask for percent, make sure you put percent, and it is a percent, okay? What you would hate to do is like put 0.016 divided by 15 and then write that as your answer. And that would be a fraction. That wouldn't even be a percent. If you put that, that would not be the percent. You got times 100 to get 0.11%. Okay. All right. So let me see. I think it's got one or two more things to show you here. So the next question here. Was letter C. Letter C, again, part 1. I don't know why I did C twice. Oh, a 1 molar solution of CH3NH2. Oh, and this is the last one. And list all the major species present. Calculate pH of a solution. Oh, let me first jump to letter D, and then I'll go backward into the other one. This one says, forget the identification. Calculate the pH of a mixture that is 2 molar lithium hydroxide and 0.50 methylamine. Guess what? That's a strong base, and that's a weak base. So ignore the weak base. Assume that the OH produced from methylamine is insignificant. You write that down, and then just say, assume the OH is insignificant for methylamine, and just find it for 2 molar LiOH. And let that be your find. Of course, you'll find the OH negative. Then from that, you can find the POH, and then subtract from 14 to get pH. Or you can, you know how to do that. Okay, but that's again one that I don't think is going to happen, or it could be on a multiple choice or something. That would be more likely than the one that was, that I skipped earlier in this lesson. That would be more likely for a base one, have a strong base and a weak base mix, and you only have to look at the strong base. Okay, but let me do this one. Let's find the pH of a 1 molar methylamine solution. And you know what? At this point, what I'm going to do, I think some of you might be able to stop the video and do the work right now. There's actually one like this on your homework, and if you do the one on the homework like I'm doing now, and you can't get it right, you can come back and watch the video if you want to save a little bit more minutes. But I'll try to go kind of quick through it. Okay, so this is CH3NH2. Let me move it up here. It seems like I'm starting really low and lower, and I'm running out of space. CH3NH2 and water gives you CH3NH3 plus and OH negative. Now, ice that baby, and it says 1 molar. So you had 1 molar of this. Of course, these are 0 at the beginning. Minus X plus X plus X. Oh, it's going to be a quick one with a 1. Okay, there's your ice box. If you want to put a box, you can. Write the KB expression. So that will be methyl amine. I guess maybe it's probably called methyl ammonium ion, I guess. Times OH negative. You don't have to even know that bit. And by the way, I don't know if I ever told you in CH3 and H2, you're pretty safe. Maybe on a multiple choice, they could ask you something about nomenclature. But they generally on the AP don't ever ask you to name anything. But what they do is they give you a name and expect you to know how to write the formula or the structure, organic structure, or whatever. So they could say aminomethane, and they'd expect you to know how to write that down, aminomethane. But now they wouldn't say, what's the name of that? So maybe it's easier if they give you the name. And that's true for pretty much every chemical, all right? But, you know, again, multiple choice, they could do it. They could do it for some stuff, like which one is copper 2 phosphate or something like that. Or no. What's the name of this compound below? Copper 1 phosphate, copper 2 phosphate, copper 3, you know. They could ask you something like that, I think. I don't know. I can't remember right off. We don't always see the multiple choice. All right, KB. Here we go. 4.38 10 to the negative 4 is equal to, at equilibrium, x times x times 1 minus x. Okay? I'll assume x is negligible. I guess I can at least put is. That'll make some English teachers happy. Assume x is negligible. All right? And so that means 4.38. So really, you can make your English teachers mad by just doing assume x negligible, and make your math teacher mad. Oh, I haven't done this in a while. Approximately. Whenever you say x is negligible, it's even better to put approximate sign after it. I forgot about that. Because that like double, it like, if you were to forget to say this statement, but you did that, then I think you'll be okay. But I wouldn't take a chance and put that only. But if you always get in the habit of doing both of these things after x is negligible, then write, if you get in the habit of doing that always, then I think you're double safe. Oh, it'll be 1, okay? And the math becomes very easy. That's just going to be 4.38 again. X squared, because that times 1. Okay, so to get the square root of both sides, and let's just see what that is. 4.38, 10 to the negative 4, and it's 0.0209 molar equals x. Okay, and the question was to find, we're just going to just do that one that says find the pH. So now we'll do it. So that is, all right, what did we just find? We found the OH negative. And let's just make sure I keep wanting to not type the wrong numbers in here. I surely hope I catch any mistakes when I do that. 4.38, 0.0209, correct. That equals OH negative. You know, that could be so important that you just put that on your question. Just that equals X equals that. Because that means so much that they know that you found OH negative. Hey, if time ran out on the AP and you had that written down, that would complete, that would be like, wow, they knew all of this, they knew how to get OH, all of this 1 or 2 steps away. So that might get some part credit. So you could do this. POH is negative log of OH negative. .0209 log negative is 1.36 figs there, so 3 after the decimal in the POH, just like pH. 679.680 it looks like. 1.680 is the POH, so now the pH will be 14 minus 1.680. I'll do it in this non-algebra kind of form, equals the pH. So if that's 1.680, 14 minus that is the pH. So 12.26 figs now, 32. So this equation does limit you. Well, the POH equation and pH equation, it says 14.00, so technically it should be 12.32 because you shouldn't have an extra O than that. There it is, 12.32. I was going to check one thing out real quick. if I did it the other way around. 0.0209. Well, if I found the, oh no, I'd have to find the H plus to get the H plus. Yeah, 12.32 is right. Yeah. Okay, 12.3, 12.32. Okay, and then percent ionization. I mean, is it really needed to do here? But I guess percent ionization would be 0.0209. That was your original, and that was your OH negative. Divide by your original 1 times 100. So 0.0209 times 100, which is 2.09%. And I think I told you before, actually 2.1%. So there's 2 sig figs there. I think I told you before, you can only say assume X is negligible when the percent ionization, percent dissociation is 5% or less. And it is 5% or less here. On the AP 1 year, they gave a problem that was like 9%. And they still didn't, they still allowed you to do it this way, even though you broke the 5% rule, because they made the problem wrong themselves. If it's more than 5%, you're supposed to then go back and do this without assuming X is negligible, doing the quadratic equation, which gives you 2 solutions and all that. Only one will make sense anyway. But what a pain. But what a good thing that you don't have to ever worry about it. But just so you know, I mean, I don't know. They could ask on the AP, why are you allowed to assume X is negligible? Why? Because it meets the 5% rule, and you could show them that 5 or less. They've never required the quadratic. So if they ask you that question, they're not going to be like, are you? They could say, would you be allowed to use? Would it be a good estimate for this one to use the assume X is negligible? Is it safe to assume? And if it were above 5, you say no, you shouldn't. You should use the quadratic. But they're not going to actually make you do it. The quadratic. Okay, that's it. So the problems were to do number 1, 2A, and 2C, and then number 3, but not the other part of the worksheet. That goes with the next lesson, which you'll see later on. I'll see you guys later on.